So what if even the most sophisticated AI systems, the ones designed to collaborate and solve these incredibly complex problems, what if they're actually feeling us? Maybe more often than we realize.
Hmm.
We spend so much time marveling at what a single large language model can do, right? But when we start combining them into multi-agent systems, well, it often introduces surprising and sometimes, frankly, kind of puzzling new challenges.
Yeah, that's spot on.
So today, we're diving into a really groundbreaking study. It's from UC Berkeley and its collaborators, and it systematically unpacks why these multi-agent LLM systems, let's call them MAS, why they often fall short.
That's right. And our core mission here in this deep dive is really to pull out the most important insights, from sources like this key research paper and the related materials. We want to help you understand the unseen complexities behind these MAS failures.
Okay.
We'll explore the common pitfalls, what researchers are doing to categorize them systematically, and crucially, what this all means for building AI that's actually reliable. It reminds me of that quote from the Berkeley researchers, which I think really hits the nail on the head. Successful systems all work alike. Each failing system has its own problems.
That's quite a statement. Okay, so let's unpack this a bit. When we talk about a multi-agent LLM system, what exactly are we talking about?
Good question. So at its core, you can think of an LLM-based agent as a kind of specialized, context-aware AI.
Ah.
It's like an artificial entity that's given a specific role, maybe some initial instructions or prompts. It has a memory, usually it's conversation history or state, and critically, it can interact with its environment using tools.
Got it. So that's the agent and the multi-agent system.
Right, so the multi-agent system, or MAS, takes a bunch of these individual agents and basically orchestrates them. The big idea, the grand vision, is collective intelligence.
Collective intelligence. How?
Well, by decomposing tasks, parallelizing the work across different agents, isolating context so specialists can focus, and hopefully fostering diverse ways of reasoning about a problem.
And these have some pretty ambitious applications, right? I mean, we're talking software engineering, drug discovery.
Absolutely. Software engineering, drug discovery, complex scientific simulations, even general purpose assistants that can handle, multi-step real-world problems. That's the potential.
Okay, the potential sounds huge.
But yeah, here's where it gets really interesting. Despite all that theoretical promise, and let's be honest, a lot of enthusiasm in the field, these MAS often show surprisingly minimal performance gains compared to just using a single agent. Sometimes not much better at all.
Minimal gains. I thought the whole point was synergy.
You'd think so.
Yeah.
But in fact, empirical analysis, like in the study, reveals some shockingly high failure rates. And this is for systems considered state-of-the-art open source MAS.
Wow. Okay, we need some examples here.
Yeah.
High failure rates. How high?
Well, let's look at the study. Take ChatDev. It's designed to model a little software company, design, coding, QA, the whole thing.
Right.
It only achieved 33.3% correctness on its programming tasks.
Only a third. Okay.
Then there's AppWorld. This uses agents that can call tools, managed by a supervisor, for everyday things like email or Spotify. It failed. Get this 86.7% of its cross-app test cases.
86.7. That's almost always fail.
Pretty much. And one more, HyperAgent. This one's a hierarchical system for software engineering, a central planner directing other agents. It failed on nearly 3/4 of its problems, a 74.7% failure rate.
Okay, those numbers are genuinely startling. Was this level of failure expected, or was this study a real eye-opener even for researchers?
Oh, it was definitely eye-opening. Even for people deep in the field, it really, really begs that critical question. Why? Why do systems with these sophisticated designs using powerful LLMs underneath fail so often?
Right. It can't just be the LLM itself then.
It suggests something deeper is going on, something about the system, the interaction.
And to answer that why, the researchers did this systematic evaluation, leading to MAST.
Exactly. MAST, the Multi-Agent System Failure Taxonomy. It's the first really systematic attempt to categorize how these systems fail by looking closely at their execution traces.
And how did they build this MAST? What was the process?
They used a method called grounded theory. It's a qualitative research approach where you build the theory directly from the data, not start with a hypothesis.
Okay.
So they meticulously analyzed over 200 conversation traces from 7 popular MAS frameworks. This involved 6 expert human annotators digging through these logs, identifying and classifying the failures.
That was painstaking.
It was. And definitely not a quick process. It involved iterative refinement, multiple rounds where the annotators compared notes, discussed disagreements, and honed the definitions. They achieved a really high Cohen's kappa score of 0.88.
0.8? What does that mean in practical terms?
In qualitative research, a kappa score of 0.88 indicates almost perfect agreement among the experts. It tells you the categories they developed are robust and consistently identifiable. It speaks to the rigor.
That's incredibly thorough. And I read they also built an LLM as a judge pipeline to make this scalable.
Exactly. They trained an LLM to automatically classify failures according to MAST. They validated this against the human annotations and got a Cohen's kappa of 0.77.
Still pretty high.
Yeah, 0.77 represents substantial agreement. It means the LLM judge is pretty good, validating its use for analyzing more traces automatically in the future.
Does MAST actually work beyond the systems they initially studied? Does it generalize?
That's another impressive part. They tested it on completely new, unseen MAS frameworks like OpenManus and Agentic 1, and even on different kinds of benchmarks like MMLU and GAIA. And it generalized really well. They achieved a Cohen's kappa of 0.79 on these new systems. Again, substantial agreement. It shows MAST isn't just specific to a few frameworks, it's a broadly applicable tool for understanding MAS failures.
Okay, so MAST gives us this structure.
Yeah.
It identifies 14 distinct failure modes, but they're grouped into 3 main categories, right?
That's correct. 3 overarching themes emerge from the data.
Let's break them down. What's the first one?
The first, and actually the largest category, accounting for about 41.8% of failures, is specification issues. Think of this as problems baked into the system design itself.
Specification issues. Like, the instructions weren't clear.
It can be that, yes, poor or ambiguous prompts, but it also includes more fundamental flaws in the system's design decisions, problems with how conversations are managed, or agents violating constraints they were supposed to follow.
So these are problems decided before the system even starts running.
Exactly. They reflect pre-execution design choices, even if you only see the failure happen during execution.
Okay, can you give some concrete examples from the study?
Sure. One failure mode is FM 1.1, disobey task specification. Pretty straightforward, the agent just doesn't follow the instructions.
Like the Wordle example.
Precisely. Chat dev was asked for a standard daily Wordle game, meaning the word should change. They even clarified this. But the code it generated used a fixed dictionary. It just didn't follow the spec.
Okay, what else falls under specification issues?
Yeah. There's FM 1.3, step repetition. Basically, the system gets stuck in a loop redoing things it already did.
Like that hyper-agent example.
Right. The navigator agent internally figured out a solution but somehow failed to communicate it properly, so the system just kept doing unrelated search steps over and over, pointlessly.
Frustrating. Any others?
FM 1.4, loss of conversation history. This is about unexpected context truncation. The agent forgets what happened earlier.
Right, like forgetting it already decided not to use a certain library.
Exactly, that hyper-agent executor case. It switched from light GBM to logistic regression because a library was missing, but then later, having lost that context, it went back to trying to install light GBM again. Wasted effort.
And one more?
FM 1.5. Unaware of termination conditions. Here, an agent just keeps going even when the task is done, or maybe even when it's impossible to solve.
Like the math agent that kept asking to continue?
Yeah, that AG2 math agent.
Yeah.
It correctly figured out a problem was unsolvable because information was missing, but it just kept prompting to continue the interaction anyway.
Okay, so that's quite a range of design-related flaws.
Yeah.
What's the big insight here?
Well, what's really fascinating, and this is insight 1 from the study, is that these failures to follow specifications aren't just about how good the LLM is at following instructions.
Oh.
It often comes down to better MAS design. They did intervention studies like improving the role descriptions for agents in chat dev. And just by doing that, they saw a solid 9.4% increase in the success rate.
Wow, with the same underlying LLM.
With the exact same LLM. It really highlights how much the system structure, the way the roles and prompts are designed, impacts performance independent of the base model's raw ability.
That is a powerful point. It really emphasizes the design aspect. Okay, so that's category 1. What's the second major category?
Category 2 is inter-agent misalignment. This covers issues in agent coordination and accounts for about 37% of the failures.
Misalignment. So this is about how the agents interact during the task.
Precisely. It covers breakdowns in how they communicate or fail to communicate, how they collaborate, or maybe how they exhibit conflicting behaviors that stop them from working towards the shared goal.
Like a team that's just not on the same page?
Exactly like that.
What are some examples here?
Well, there's FM 2.2, fail to ask for clarification. An agent gets ambiguous input but just plows ahead with wrong assumptions instead of asking.
Like the App World Spotify example.
Right. The Spotify agent needed an access token. The supervisor gave it a password. The agent should have clarified, hey, is this the right format? But it didn't. Task failed.
Okay, what else?
FM 2.3, task derailment. This is when an agent just goes off track, deviating from the actual objective.
Like the math agent solving the wrong problem.
Yeah, that AG2 agent solved the first problem correctly, then just veered off and started solving a completely different one.
Huh, weird.
Then there's FM 2.4, information withholding. An agent has a crucial piece of information but fails to share it with others who need it.
Like the phone number example.
Exactly. The phone agent figured out the username should be a phone number but didn't tell the supervisor, so the supervisor kept trying to log in with the wrong thing. Repeatedly.
Inefficient and ineffective.
Absolutely. We also see FM 2.5 ignored other agents' input. Pretty much what it sounds like: one agent points out an error or provides info, and another agent just ignores it.
Like the peer review case.
Yes, in that multi-agent peer review setup, one agent spotted an error in another's work, pointed it out, but then the first agent just disregarded the correction and stuck with its own wrong answer.
Stubborn AI. And the last one in this category?
FM 2.6. Reasoning action mismatch. This is subtle but important. There's a gap between the agent's internal thought process or reasoning and what it actually does or communicates externally.
Like the HyperAgent Navigator, finding the fix but saying something else.
Right. Internally, its trace showed it found the right fix for a pilot bug, but what it communicated to the planner agent was irrelevant, just delaying the actual solution.
So diagnosing these misalignment failures sounds tricky.
It can be really complex, yeah. Because sometimes different root causes like poor communication versus actively ignoring input can look similar on the surface. That's why having these fine-grained MAST modes is so valuable. They help you pinpoint the real underlying issue.
Okay, that makes sense. So we've covered specification issues and inter-agent misalignment. What's the third and final category?
The final major category is Category 3, task verification, which is essentially about quality control. This accounted for about 21.3% of failures.
Task verification. So this is about checking the work.
Exactly. These failures happen when the verification processes are inadequate, they don't catch errors, or they don't correct them, or sometimes the task just ends too soon before proper checks are done. It highlights problems in ensuring the final output is actually correct and reliable.
Okay, examples.
Well, there's FM 3.1, premature termination. The task just stops before everything is truly finished and verified.
Like the Flask bug example.
Right, with HyperAgent. The editor agent claimed it had fixed a bug in some Flask code. The system terminated. But when the test script ran, it failed because the change hadn't actually been applied correctly. The task ended based on an unverified claim.
Oh,
FM 3.2. No or incomplete verification. This is a big one. The system either doesn't check the outcome at all, or the check is just superficial.
Like the chat dev chess program.
Exactly. It generated a chess program. The verification checks passed. Maybe it checked if the code compiled, if the basic structure was there. But it contained runtime bugs, like letting pieces make illegal moves. The verifier didn't check against the actual rules of chess.
So it passed the superficial checks but failed the real test.
Right. Or another example from AG2, a math agent confused the number of fish someone bought with the cost per fish. It got the final total wrong, but there was no proper verification step to catch that logical error.
And the last mode here.
FM 3.3, incorrect verification. Here, a verification process exists, but the process itself is flawed. The check is wrong.
How does that happen?
In a MetaGPT chess implementation they looked at, the initial tests written by an agent failed to cover movement restrictions for pieces like knights or bishops. So the code passed the tests, but the tests themselves were incomplete, giving a false sense of correctness. The verification itself was incorrect.
Got it. So with verification being the final check, what's the key insight for this category?
This leads us to Insight 2. Multi-level verification is absolutely needed. Verifiers are crucial, don't get me wrong. Systems that have explicit verifiers generally do have fewer total failures.
Okay, so they help.
They help, but they're not a silver bullet. Current verifiers often just do these superficial checks. Does it compile? Does it look roughly right?
Right.
Robust MAS, the study argues, need multi-level verification. That means integrating external knowledge, having rigorous testing throughout the generation process, not just at the end, and checking both low-level things like code correctness and high-level things like whether the overall task objective was met.
And did they test this idea?
They did. They ran an intervention in chat dev where they added a specific high-level check for the main task objective. And that alone yielded a really notable 15.6% absolute improvement in task success.
13.6% just from adding a better verification step.
Yep. Shows how impactful proper layered verification can be.
Okay, so across all three categories, specification, misalignment, verification, it really sounds like the system's structure and processes are critical for getting things right. But you mentioned earlier, it's not just about correctness, is it? The study found something else.
That's right. Beyond just getting the answer wrong, the study revealed another pervasive problem: inefficiency.
Inefficiency, how so?
Well, agents often get stuck in these unnecessarily long conversations, or they take really roundabout ways to achieve a goal.
Okay.
And this leads to dramatically increased costs, we're talking token usage for the LLMs, and much higher latency, meaning runtime, sometimes by factors of 10x or even more.
10 times longer or more expensive.
Wow.
Can you give an example?
Sure. There was one app world trace they analyzed. The task was simple: get 10 songs from a specific playlist.
Okay, sounds straightforward.
But the Spotify agent and the orchestrator agent ended up having 10 separate rounds of conversation, retrieving just one song at a time.
One song per round, but surely the API.
Exactly. The API allows retrieving all 10 songs or even more in a single action. But the way the agents were set up or communicated led to this incredibly inefficient back and forth.
That's kind of maddeningly inefficient.
It is. And while NMA, the taxonomy we've been discussing, currently focuses mainly on correctness failures, these efficiency concerns are absolutely critical for making these systems practical in the real world. Nobody wants an AI assistant that takes 10 times longer than necessary.
Right. That's fascinating. It's like having a team of brilliant people who are just completely bogged down by bad process or endless meetings, taking forever to do something simple. So pulling this all together, what's the bigger picture takeaway here?
I think a truly crucial finding, maybe the most important one, is that so many of these MAS failures, both the correctness ones MAST categorizes, and these efficiency issues stem from fundamental problems in system design.
Just in design again.
Yes, and related challenges in sort of organizational design for the agents and how they coordinate. It's not solely about the limitations of the individual LLMs, like, hallucination or not knowing a fact. Those happen, but they're not the whole story, maybe not even the main story for MAS failures.
Right. It reminds me of that idea that even an organization full of really smart, capable people can fail completely if the structure, the communication, the processes are just fundamentally flawed.
Exactly. So while getting better base LLMs is always good and helpful, this study strongly suggests that better LLMs alone are not enough. They won't automatically guarantee reliable or efficient MAS performance.
So we need more than just smarter agents.
We need more fundamental changes, it seems. Changes in how agents are organized, better communication protocols, more robust context management and memory, and, as we saw, much better integration of verification throughout the whole process.
Okay, so this brings us to the practical side. How can developers or researchers actually use MAST? Is it just an academic classification?
No, not at all. It's designed to be a foundational framework, yes, but also a practical tool. It helps in understanding, debugging, and ultimately improving these MAS.
How does it help practically?
Well, by providing this structured vocabulary, these specific definitions for different failure modes, MAST-PLE allows for systematic diagnosis. Instead of just saying it didn't work, you can pinpoint why.
Okay.
And with tools like the LLM annotator they developed, developers could potentially get a detailed breakdown of the failure types happening most often in their system.
So it guides debugging.
Exactly. It points you towards the highest impact areas. For instance, the study's data, shown in their figure 4, suggests that someone working on HyperAgent could get significant improvements by focusing specifically on fixing step repetition, FM 1.3, and incorrect verification, FM 3.3, because those were particularly common for that system.
I see. And what about solutions? Does MAST suggest ways to fix these problems?
The research talks about distinguishing between tactical approaches and structural strategy.
Tactical versus structural.
Yeah. Tactical fixes are things like tweaking prompts, maybe minor adjustments to conversation flow, quick fixes.
Okay.
Structural strategies are deeper changes. Implementing comprehensive multi-level verification like we discussed, designing standardized communication protocols between agents, improving memory systems, fundamentally changing the agent organization.
And which approach works better?
Well, the study found that while tactical fixes can offer some improvements, they saw some gains in the AG2 and ChatDev case studies from tactical changes. These fixes often proved inconsistent or just weren't sufficient for major gains.
So the quick fixes aren't enough.
Often not. It really underscores the need for those more robust structural changes to build truly reliable systems. It kind of drives home that you need to look at the overall blueprint, the system architecture, not just keep patching the leaks as they appear.
Right. Makes sense.
Hmm.
So wrapping this up then, we've seen that multi-agent LLM systems, MAS, they hold this really immense promise, but their widespread adoption really hinges on making them reliable and efficient.
Absolutely.
And this MAST taxonomy, it offers a powerful new lens, a structured way to understand exactly why they fail. It moves us beyond just saying the AI messed up to getting concrete, actionable insights that are often rooted in system design and agent coordination.
Precisely. This systematic approach, identifying these specific failure modes, it really provides a clear roadmap for future research and development in the area. It tells us we need to focus on building robustness and efficiency right from the ground up into the system's design, not just trying to fix symptoms later.
Okay, so as you, our listener, reflect on this deep dive, here's maybe a final provocative thought to chew on. If knowledge truly is power, how do we make sure that these increasingly intelligent, increasingly collaborative AI systems we're designing are not just capable, but are also reliably, though wise in how they work together? From everything we've discussed, what stands out to you as the most crucial step we need to take towards building these reliable multi-agent futures?